Okay, so in our previous session, you will recall that we worked on this question 1.1.1, whereby we were dealing with factorizing. So we spoke about the four techniques of factorization: the common factor, difference of two squares. We spoke about factorizing trinomials, and then lastly, we spoke about grouping. So we did all of this, that one, and that one previously. Today, I want us to continue. So today we are working with 1.2 and 1.3. So basically today we are simplifying algebraic expressions. Now, what does it mean to to simplify? Okay, what does that mean? What does it mean to simplify algebraic expressions? Okay, so 9 times out of 10, when we are required to simplify, it's basically the opposite of factorization. Remember, when we're factorizing, our goal was to take an algebraic expression and express it as a product of its factors, right? But then when we are simplifying, we're taking something of this sort, which is clearly in its factorized state, or it is written as a product of its factors. But then now what we want to do is we want to break it down in a way that it becomes a single algebraic expression. For example, something of this sort, you know. So that is the principle of simplification. It is simply the opposite of factorization. So let's get into it. Let's get into it. So we can start with 1.2.1. Question 1.2.1. So it says we must simplify this situation: x plus 2 into x squared minus x plus 3. Okay, so as I've indicated before, we need to multiply this thing out in such a way that we will only end up with a single algebraic expression. So how do we do that? We simply distribute whatever that is in here, we multiply it with everything that is in there. Okay, what do I mean by that? I'm talking about this. Take this, we multiply it with that guy, multiply it with that guy, and multiply it with that guy as well. Take this, multiply it with this guy, multiply it with that guy, and then you multiply it with that guy as well. So that is basically what we are going to do. So let's do it. X times x squared will give us x to the power of 3. X times minus x will be negative x to the power of 2. X times 3 will be positive 3x. And then we come to that guy. We say 2 times x squared gives us 2x to the power of 2. 2 times minus x gives us negative 2x. And then 2 times 3 gives us positive 6. Continuing. Now, what we need to do is we need to add all the like terms, okay? So this and this, they are like terms. Let's see, this guy and that guy are like terms, and then this is no like term, and so is this constant. They do not have any like terms, so they won't be added to anything, okay? So x cubed, and then we deal with these like terms. Negative 1 plus 2 will give us positive 1. So it will be positive x to the power of 2. And then 3x minus 2x will give us positive x. Yes, positive x. And then 6 is just 6 plus 6 like this. And now we are done. So this is the simplified version of this expression over here. So we are done. We can continue. Now we are doing 1.2.2. So 1.2.2 is a bit different. They want us to simplify this situation, 5 over x plus 3 minus 3 over 2 minus x. Okay, so we have a situation like this in 1.2.2. Okay, so what do we do in this particular situation? So you will remember back then when we were still in primary school, we dealt with fractions, like the adding and subtraction of fractions. We dealt with this. So let's say we have a situation whereby, this is a negative sign. Let's say we have a situation whereby we have a over b minus c over d. So the principles that we established back then was that the first step is to find what we call the lowest common denominator, the LCD. So how do we do that? We simply multiply the two denominators. So our LCD will be b times d, which is simply bd. Okay, so that is the first step. And then we ask ourselves, Uguchi, what did we do to this b in order to convert it to become bd? The answer is very simple. We multiplied it by d. Okay, so the rule of dealing with fractions is that whatever that you do in the denominator, you have to do the very same thing in the numerator. So by that, we must multiply the numerator, which is a, by the constant d. Okay, and then we do the very same thing. So this has been multiplied by d. So now we have to do the very same thing this with this second fraction. So we ask ourselves the very same question: what did we do to d to convert it to become bd? The answer is very simple. We multiplied it by b. And then because we did that in the denominator, the rule of fractions requires us to do the very same thing in the numerator as well. So what do? We multiply the numerator by b also. Okay, so it will become b c. Okay, so this principle that we learned in grade 6 or something like that, grade 5 or grade 6 of mathematics, is the very same principle that we will apply when we are dealing with algebraic fractions, right? It's the very same principle that we are going to apply. So the idea is we want to convert this situation into a single fraction. So that is the simplification that we are going to do. We are going to convert this guy into a single fraction. And by doing that, we have to apply the algebraic techniques that we established in earlier grades. Okay, so that's that. No, let me get rid of just this. Okay. All right, with that being said, let's apply what we were talking about. So as you've seen, the first step is we need a lowest common denominator, and we get that by simply multiplying the denominators that we are working with. So we simply do this, and then according to the laws of fractions, whatever that you do at the bottom, we have to do at the top as well. So this guy has to be multiplied with this denominator. Okay, 2 minus x and then minus 3. That guy has to be multiplied with this other denominator, which is x plus 3. Okay, and then we can simplify. Simplifying, it will be 5 times 2, which is 10. 5 times minus x, which is minus 5x. And then minus 3 times x will give us minus 3x. and then minus 3 times positive 3 will give us minus 9. Divide, and then it will be x plus 3, 2 minus x. Okay, so we see that in our numerator we have like terms, so this is a like term with that guy, and also we have like terms as our constants, so we can simplify our expression further. 10 minus 9, that is positive 1, and the negative 5 minus 3 is negative 8, so it's negative 8x divided by x plus 3, 2 minus x. Okay, so we are done with the simplification. I mean, if you want, you can you can multiply the denominator out, and then you'll end up with a quadratic expression in the denominator, but then that will not make any difference because it will not simplify the expression any further. So even if you leave it like this, it is still correct. Okay, so we are done at this point. We now go to 1.2, 1.2.3, 1.2.3. Going to 1.2.3, we are required to simplify this guy times 15 to the power of x plus 3. Okay, the power of x plus 3. Let's remove this guy over. That should be divided by 3 to the power of x times 5 to the power of minus x. Okay, so we see that we have a situation whereby we have a lot of exponents, right? So if we are dealing with exponents, it is very important for us to bear in mind the exponential laws or the laws of exponents. Let's just review very quickly what I mean by the laws of exponents, like the basic laws of exponents. So let's say I have a to the power of 2, and I'm multiplying it with a to the power of 3. According to the laws of exponents, I must do this, or I can do this. So my results or my answer will have one base, which is 1a, and then to obtain the power, I'll simply add the powers of these two. So it will be 2 plus 3, which will give me 5. Okay, so this is my answer according to the laws of exponents. And then, so what does this tells me? It tells me that if I am multiplying two exponents to the same basis, what do? I simply write the base ones, and then I can add the powers. That is my solution. And then what if I have a situation like this? I have a division sign in this particular case. So basically I'm saying a to the power of 3 divided by a to the power of 1. What do I need to do? So according to the laws of exponents, we write the base ones and then we subtract the powers in this particular case. So I will have 3 minus 1, which will give me 2. Okay, so that is my final answer in this particular case. Okay, so the laws of exponents tell us that. And then another law that is of valuable importance is that if I have a situation like this, a to the power of 2, um, times b to the power of 3, and then I have a bracket, and then I have a power on the outside. Let's call it 4, for example. So what happens is that I can take this power and distribute it to that guy and distribute it to that guy as well, because it belongs to both the terms A and B because it's outside the brackets, okay? So with that being said, this can be simplified to a to the power of 2 times 4. 2 times 4, where does the 4 come from? It comes from the outside, okay? And then b to the power of 3 times 4. And then this can be simplified, and then we can say that a to the power of 8 times b to the power of 12, okay? So this is the equivalence, or this is the same as that guy. So we have used the laws of exponents, or one of the laws of exponents, to simplify this particular case. Okay. Another law that is of significance is this: that anything raised to the power of zero is one. Okay. And then another very important law is this law that if we raise anything to a negative power like this, what we can do is I can just do this and say 1 over, and then it becomes a positive power like that. So we call this the inverse law. So if we have something that is raised to a negative power, we can simply say 1 over that, and then it changes the sign of the power from positive to negative. Okay. So that can be done. And yeah, hopefully I've covered all the laws. Okay, so very important to note. It's very important to note. I know that we are used to applying the laws this way, in that direction. But then, since this is an equation, it means that the laws can be applied in that direction as well. What do I mean by that? I mean, if I have a to the power of 5, if I'm starting with a to the power of 5, I am allowed to express this as a to the power of 2 times a to the power of 3. Okay, so this is what I mean. The fact that we are starting on this side going that way doesn't mean that I can't start with a to the power of 5 moving that way. For the fact that there's an equal to sign, it means that whatever that is here is the same as whatever that is here is there. Doesn't matter if I start with this guy or the other guy. Okay, hopefully that makes sense. And this very same principle can be applied to all the laws that I have stated here. Okay, so hopefully we have a good foundation in terms of the laws of exponents. So now we can go and apply them to our question. Okay. Okay. So what can we do to simplify this, or to to make it as simple as possible, basically? We saw that we have a a number of laws that can aid us in the simplification of this particular expression. So what I'm hoping for a situation like this whereby I have one thing as a numerator, and then I have another thing as the denominator, and these things are exactly the same, and then because of that, I can be able to cancel them. So this is what I am hoping for in order to make this particular situation to be more simpler. Okay, so I am hoping and praying for this kind of situation. Okay, so let's make it happen. So we see that in this guy we have 25, but then in the denominator we have bases like 3 and 5. So initially there's nothing to cancel of 25 word. Okay, but then if we can write 25 such that the base that will be associated with 25 is the very same base that is present in the numerator, in the denominator, I mean, then we can be able to cancel stuffs out. Okay. The same thing applies to 15. If we can find another way of writing 15 such that we can be able to cancel it with one of the exponents that are present in the denominator, then that will be useful. Okay, let's get it done. 25 can be written as 5 times 5, or you can say 5 squared. It's completely the same thing. Okay. And then we can write 15 as 3 times 5 raised to the power of x plus 3. Okay. And I'll say equal to, before we say that, we have a denominator. Okay. Denominator is 3 to the power of x times 5 to the power of negative x. Okay, and then from there, we saw from one of the laws of exponents that if we have a power on the outside like this, then the power can be distributed by multiplying it with the powers of the inside, right? So there's a power of 1 here, there's a power of 1 there. So we can simplify and say this is actually 5 to the power of negative x times 5 to the power of negative x. Okay, and then we can say we can do the very same thing in this situation because there's a power of 1, there's a power of 1. We will basically take this power, which is x plus 3, we distribute it here, we distribute it there, and then we will result in a situation like this: 3 to the power of x plus 3, okay, times 5 to the power of x plus 3, okay, and then we can divide. We can say that this is divided by x, 3 to the power of x times 5 to the power of minus x, and then that is what we have at this point. Okay, now we see some interesting things because we can see that this guy is present there, but then it's also present in my denominator, and that is music to my ears because I want to cancel stuff out. So this cancels with that one, and now I have made my life more easier. Okay. Um, and then we we see a situation here. Now let's talk about this situation here, that situation, and that situation. Right now, if I do this, then I am totally violating the laws of exponents because this is not exactly the same as this. But then there's something that we can do to this guy that will result in something that can cancel out with that guy. Okay, let's make that happen. So 3 to the power of x plus 3 can be written as 3 to the power of x times 3 to the power of 3. Remember, I said that the laws of exponents, they work in that direction, but then very importantly, they also work in the reverse direction because of this equals to sign. Okay. Okay, with that being said, you can continue. And then we can say that 5 to the power of x plus 3. Okay. And then we can divide by 3 to the power of x. And then now we see something very good. This is the same as that, so we can cancel them out. Okay. So if we continue, we'll see that we are left with 5 to the power of negative x times 5 to the power of x plus 3 and multiplied by 3 to the power of 3. Okay, so this situation, this one, it reminds us of the situation that said a to the power of 3 times a to the power of 3, a to the power of 2, I mean, times a to the power of 3 is the same as a to the power of 5, whereby we simply just added the the powers because the bases of our exponents were the same. Okay, so we will take that very same principle and then we'll apply it in this particular situation. So let's get it done. Okay, getting that done, we will take one base, which is 5, and then we will simply add the powers. So it's x plus 3 times 3 to the power of 3. And then what will happen is that we will simplify. So negative x plus x will give us 0. So we'll just be left with 5 to the power of 3 times 3 to the power of 3. So basically, we have a situation whereby 5 to the power of 3, we know it's 125, and then 3 to the power of 3 is 27, if I'm not mistaken. And then we can simply multiply the two of them and see what do we get as a result. So 125 times 27, that gives me 3375. So this is basically my final answer. So now the question that we are working with is 1.3. So in 1.3, they said that they say we must determine the value of 3p plus q all squared if 9p squared plus q squared is 12 and p times q is minus 3. Okay, let's get it done. We are now busy with 1.3. Okay, we're busy with 1.3. They said they want the value of 3p plus q all squared, and then they give us some information that 9p squared, okay, plus q squared is 12. So this is the first given information, and then p times q or pq is minus 3. Okay, so what we are going to do here, we'll simply break this down, and then at the end we will incorporate or we will involve the given information to see what is the numerical value of this particular expression. Let's do it. So basically 3p plus q, and then we say times 3p plus q, okay, because of that squared. And then we simplify it, this times that times that times that, and that times that. Okay, let's do it. 3p times 3p, we get 9p squared. 3p times q, we get 3pq. And then q times 3p, we get 3pq. And then q times q, we get q to the power of 2. And then we see that this guy and that guy are like terms, we can add them. 9p squared plus 6pq, okay, plus q squared. Yes, so this is our final simplified expression of this guy. Okay, so with this being said, we are given some interesting information. We are given that 9p squared plus q squared is 12. Okay, so we have 9p squared plus q squared. So that is 12, and then they told us that p times q is negative 3. So q, this part is negative 3. Okay, so we can change the order just to make it more obvious. 9p squared plus q squared, and then we can say plus 6pq. So what I'm saying is that this part is the part that is equal to 12. Hopefully you can see that. And then PQ is the part that is equal to 3. So we can simplify this by substituting in the numerical values and then hence determine the numerical value of the given expression. So this is 12, okay? P times Q is given to be minus 3, so we can 6 times minus 3, that is negative 18. So we see that our expression has a value of negative 6. Okay, so it has a value of negative 6. So that is that. And so our final answer is negative 6. Okay, but then just a quick note on the given expression. So they gave us 3p plus q all squared. Now you can either simplify this thing by using the longer method, the FOIL method that I showed you, or the FOIL method that I used in this particular case, whereby you put two brackets and then you actually do the multiplication, or you can use a shortcut method that I call the SMS method. Very easy, very quick, and very effective. So basically what we do is call it the SMS method. So basically what we do is that we square the first term. So we square the first term, you get 9p squared, right? And then you multiply the two terms. So you take this guy and you multiply to that guy. So you multiply the two terms and then you multiply that product by 2, or you double whatever that you get. So it will be 3pq times 2, which will give us 6pq. Okay, so first step, you square the first term. The first term in this situation is 3p. The second step, you multiply the two terms and then you get the product. 3p times q is 3pq, and then after that you double whatever that you get, or you multiply it by 2 to obtain 6pq, and then last but not least you square the last term, you get q squared. So you can see that you can use this method to get the very same answer as that long method, and yeah, it is very effective and very time saving. Okay, so that is just one tool to add on your toolbox. So another useful thing that you can look at when you are simplifying expressions of this sort is you can look at the mark scheme. For example, if you are simplifying something like this, x plus 2 all squared for 1 mark, it's very unnecessary for you to go through all of these hoops and to do all of this just to do a question of 1 mark. So it is very valuable and very useful to know the shortcut method. And also, even if the marks that are given are indicating that you must use the long method, you can easily use the shortcut method to check if your answer is correct or not. So to ensure that you didn't make any errors during your working out. Okay, so that is very important to take note.